the half-life of a certain radioactive substance is 14 days. Suppose there's 6.6 grams present initially. Express the amount of substance remaining as a function of time. So to do that, I'm going to use my exponential model. Oops. So far, so good. So I remember that P naught is the initial amount. So that's going to be the 6.6. And I remember that my my R has to do with the percent growth or decay. Good. Since this is half-life, there's no percentage given, but I recognize that the R there needs to be minus 50, minus because it's decay, and half because it's 50%, right? If you think about like a sale, if it's half off, that's like a 50% off sale. Everybody so far so good? And then I need to pick a unit for T, right? So in the problem, it tells me that this decay is happening every 14 days. So I'm going to say that T is going to equal 1 day increments. So how much of that half-life is going to happen in 1 day? 1/14 of it, right? If it takes 14 days to do a whole one, 1 day is 1/14 of it. So my exponent will be like 14 over T. So that's my answer for A. For B, then, it's asking when will there be less than 1 gram remaining. So I just need to solve P of T equal to 1 then, right? Now to do that, I'm going to use my graphing calculator. So I'm just going to type in my equation for P of T. One plus negative 50 over 100 is just a half. That's why I wrote 0.5 there. It just was easier to type in my calculator. And then 1. Now, I have to be careful about choosing my window, though, right? So my x is representing the t, which is time. So let's think about it. I have 6.6 initially. After 14 days, that'll go down to 3.3. After 28 days, that'll go down to like 1.65. And after another 14 days, so out at 42, that'll be now somewhere under 1, right? Everybody agree? So I'm going to go from 0 to 42 because I can just kind of quickly and easily tell that it's going to get it below 1 somewhere in between then. Is everybody okay with that? You could have just guessed and written 100 there or something and it would have been fine. All I need to do is make sure I can see that intersection on my screen somewhere. I like to just kind of like work it out in my head. Now the y's are representing the amount of substance. So the least amount of substance I can ever have in a decay problem is 0 because eventually it's just all going to go away. The most I'm ever going to have is what I started with, which is 6.6. I'm just going to write 7 though because I like round numbers. And then I'm going to hit graph. So there's my decay curve. There's my line for y equals 1. That's my intersection right over there. So second trace, intersect command, enter, enter, enter. And I will get about 38.1 days. How's that feel, Mar? Is that what you were looking for? So most of it's just going to be like making sure you're filling things into the model correctly. For these story problem ones, Max?
Oh, no, I answered my question. I was confused there for a second.
Okay, Nicole?
Since for a while ago, but number 16.
16?
Yes.
Sure. Yes. Yes. Good luck with the vampires. You guys get it? Because they're going to suck her blood out. Nobody laughed at it, though. All right. 16 says, the population P in millions of people of New York State, T years after 1800, is modeled by the equation yada, yada, yada. What is the population 1850? What will the population be in 2020? What is the maximum sustainable population? Okay. So in 1850 is part A. I know that T is the years after 1800. So what is the T that I'm going to be plugging in then have to be? 50. So into my calculator, I'm just going to do like B of T. I'm just going to plug T in for, or plug 50 in for T and press enter. Is that okay, Nicole? Yeah. Okay. In part B, it asks for the population in 2010. So what is the T going to be for 2010? You mean 210? Then yes. So again, then I'm just going to plug 210 in for the T in my equation. And I don't actually have to do that in my calculator, right? You're okay?
So what we would do is you would just plug in the problem that's up there, but instead of T, we would do parentheses 50.
Sure. Yeah, you can do it that way. Yep. There's lots of ways you could put it into your calculator, but that's fine, what you described.
And is there like a button specifically for like that E, or is that just like implied?
Yeah, so if you look on your calculator, it's like if you look above the ln, there in blue, there's the e to the x, so that'll give you the e with the exponent already on it. Or if you look at the division symbol, above that in blue is also the e if you don't want an exponent attached to it.
Okay.
So either one will work. And then it asks in part C, what is New York's maximal sustainable population? So that's going to be one of the asymptotes. If I look at the P of T, I notice that's a logistic equation. So the asymptotes are always y equals 0 and y equals c. And the c is just the numerator. So the maximum sustainable population would be 19,875,000, because again, P is in millions of people. But that's basically all you need. Does that feel okay? And it's okay that I didn't actually plug into the calculator. Like you're capable. You're good with that. It's one of those, like, if you read it, oh, okay, that's all I need to do. Felt too easy. Okay, last call on questions before we move on to new stuffs. Max?
Yeah, what would A be in this problem? It's like,
what would A be?
Yeah, because isn't like the exponential. Well, no, this is a decay.
No, this is a logistic equation, not a exponential equation, because it's got the exponential part in the denominator. So logistics are not like that, where it has like an initial amount built into it. Okay. So today we're going to start 15.3. We're not going to finish this today, but we're going to start it. In 15.3, we're going to start talking about logarithms. So I want to start with something to just kind of get us used to thinking about this. So if I have 2 squared, I know that's 4. And 2 to the third, well, I know that's 8. But what if I wanted to know what is, like 2 to the what gives me 6? Well, we know how to do that on our calculator, right? We can just graph 2 to the x, and we can graph 6 and find the intersection, right? Just like we've been doing. Just looks like solving an exponential equation. So that looks like something we've been doing here recently. So if I do that, there's my intersection. So second trace, intersect command, enter, enter, enter. And I'm going to get that decimal. Let me just do that so I can look at it at the same time. And that's a little bit of a surprising result. Considering everything was like a whole number and I need this cuckoo decimal to make it work out. It turns out that this is actually an irrational number. And like for most irrational numbers, we want to create a symbol to kind of represent it, right? Whether it's like pi or e, or even something as simple as like the square root of 2 or the square root of 3, where we don't have to write the decimal forever. We want to create an abbreviation. So the abbreviation we're going to create for this number is going to be log base 2 of 6. So it's basically telling us the power of 2 that gives us 6. Okay, so these logarithms are basically going to be answers to an exponential equation, right? Like what power of this number gives us that number? That's what this logarithm is going to represent. Is everybody okay with that notion? So that's how we're going to define our logarithms. We're going to define them through as a translation of an exponential equation. So we say a logarithmic function is used to rearrange an exponential equation. So given positive values for b and x, and the b not equal to 0, the exponential equation, b to the y is equal to x, is equivalent to the logarithmic equation, log base b of x is equal to y. So it's just a way to, the definition for the logarithmic equation is just a translation of the exponential. So let's practice doing that a little bit. So let's do some example here to get used to using this definition. It's kind of like the undoing of exponents. Is kind of what this is. So if I wanted to do log base 4 of 16, I'm going to write that as a logarithmic equation. So I'm just going to say it's equal to y, so it looks just like this guy. Everybody's okay there? I'm then going to use my definition of a logarithm to rewrite this. So like the base of my logarithm becomes the base of the exponential. The argument for the logarithm is the answer to the exponential. And the answer to the logarithm is the exponent for the exponential. Everybody see how I move those numbers around to make my exponential equation? And hopefully when we recognize, or when we look at this, we recognize that 16 is 4 squared, right? And if the equation is equal and the bases are equal, that tells us the exponents also have to be equal. So y just has to be 2. Is that okay? Let's do another. So we have log base 5 of square root 5 is equal to y. Again, I just made a logarithmic equation. We'll translate that now into an exponential equation. So 5 to the y is equal to the square root of 5. Hopefully we remember that I can rewrite radicals as exponents. So the square root of 5 can just be 5 to the 1/2. And then again, I can say if the equation is equal, the bases are equal, then the exponents have to be equal. So y is just 1/2. So log base 3 of 1 over 27. So write that equal to y. Now this might be a little bit more difficult to recognize how I'm going to rewrite 1 over 27 as 3 to some power, right? Hopefully we recognize that 27 is 3 to the 3rd. So 1 over 27 is like 1 over 3 to the 3rd. So it's going to be 3 to the negative 3rd. You knew the negative had to go in there somewhere. Yeah. Yep. And so what does that tell us the value for y is? Negative 3. So the next one is log base 12 of 1. So again, we rewrite it as 12 to the y is equal to 1. And oh, well, I know this. What does y have to be? 0, right? Because I know any non-zero number to the 0 power is equal to 1. 0 to the 0 is indeterminate. That's worse than undefined. Holy smokes. And the last one, log base 8 of 8 is equal to y. Yeah, so I know that 8 is just 8 to the 1st, so y just has to equal 1. So if I look at these problems, there's some observations I can start to make, right? So if I look at problem D, any log of 1 should be 0, right? Because it doesn't matter what the number is as long as it's not 0, which it can't be because the base of the logarithm has to be greater than 0 and not equal to 1. So like log of 1 is always going to be 0. Doesn't matter what the base is. if I look at the last one, the argument of the log and the base of the log match. That's always going to give us 1, right? And then what about these guys up here? What are these guys trying to show us? Well, I recognize that like 16 was 4 squared, right? And then like they kind of cancel out and the exponent's the only thing that's left. That's kind of what's happening here, right? That log base b is canceling exponent base b, and what you're left with is just the exponent.
Okay, so we're given the start and the finish, and we gotta just try to find out what's in the middle and what this is.
Well, what I'm trying to do right now is we're trying to build like a way to think about what a logarithm is, because we don't really, it's not really clear at first what this is. But what I'm trying to show you is that the logarithm of a number is just the answer to an exponential equation, right? But it's more than just that. That's kind of our beginning understanding. So what we're hoping to get from this example is that there's some basic properties of logarithms. So we've just kind of illustrated 3 of them, and the 4th one I think we can infer from that one we just most recently did. So our basic properties for logarithms, any log of 1 is 0. You guys came up with that pretty easily. Log base b of b is 1. Again, you came up with that pretty easily. This is what we just showed you guys, that like log base b is canceling exponent base b. And if log base b cancels exponent base b, the reverse should also be true, that exponent base b should cancel log base b, right? That is just, and you're left with just the argument from the logarithm. So what we're hoping to look at from these last 2 is that exponent base and log base are similar to multiplication and division, or similar to addition and subtraction, or similar to sine and sine inverse, that they are just inverse functions of one another, that's how we cancel out the base of an exponent, or that's how we'll cancel out a logarithm is with the other. That's the way that you probably want to conceptualize these things. It's going to be really useful to be able to think about logs and exponentials this way in order to solve equations, which is where we're getting to in a day or 2, or a lesson or 2. That's kind of where we're going to head towards. Okay. So if I kind of keep moving forward. So you know how when we have like a radical, usually we put a number in here for the index, but there's one number that we never write in there. What number do we never write there? Well, we never write a 2 for the square root, right? We just leave the symbol off because we recognize that like if I don't write it there, that just means square root, the index is 2. We do the same thing for logarithms. There's actually 2 special logarithms that get their own special notation. So they are called the common logarithm and the natural logarithm. So the common logarithm, we're going to recognize every time is just base 10, and we're going to write out log with no subscript. So if you see log with no subscript, that means base 10. We've chosen to write it that way as a mathematics community. We recognize that if there's nothing down there, that means 10. Everybody okay? The other is the natural log, which is base E, and we're going to write that as ln. Now, when I write it, I'm always going to write it in cursive, because what's wrong with a print letter L in a math class? Looks like a 1. I don't want to be confused on that, so that's why I'm always going to write my logs with cursives so that I don't get confused as to what's a number 1 and what's a letter L. So in particular, the ln is a place where like students get confused and what that symbol is, and it's just, think about it as cursive. When I type out my tests and stuff, I can't put them in cursive, but when I write it by hand, I'm always going to write it in cursive. Everybody's okay? So you might have noticed on your calculator, you have a log and an ln button already built into your calculator, right? So if I wanted to do like log of 9, I just press that log button, which is right next to the 7, and then type in a 9 and press enter. Boom. Or if I wanted to do the natural log of 15, I can type the ln button, enter 15, and then press enter, and it spits out a decimal. What if I wanted to do like log base 5 of 19? I don't see a place where I can put a subscript on my logarithm here. Well, your calculator can do that. So to get that, you're going to press the math button, and then you're going to scroll all the way down till you find the log base command. And that'll allow you to do like, type any base you want there, and you could do like log base 5 of 19. Is everybody okay with that? All right. Great. Let's do a little bit of practice here using the common and natural logarithms real quick. We're going to do some more stuff by hand just to kind of get used to how we can kind of manipulate logarithms or ways to conceptualize a logarithm. And we'll talk after that about some more properties of logarithms. Oh my God, what is this? You stupid thing. All right. So when I look at the first problem, it says A equals log of 1,000. First thing I need to do is recognize what is the base of the logarithm that's written here. This is base 10. There's no base down there. I recognize that it's base 10. Have to remember that. So if I used my definition of logarithms, I would say, okay, 10 to the A equals 1,000. And I can rewrite 1,000 as 10 to the third. So I get that A is just equal to 3. And it's fine to think about it this way, and that's like the natural first way to think about it. The way that I like to do this problem is I would rather write 1,000 as 10 to the third, and then think about log base 10 and exponent base 10 canceling and just being left with the 3. I think that's a more useful way of thinking about the process. Now you're doing the exact same thing. It's just about like how you're doing this. But I think that reinforcing that like that's how you cancel one of these things out is more valuable long term than like everything having to go back to an exponential equation. Is everybody okay there? So this is the way that we're gonna do the rest of these. So again, first things first, what is the base on this logarithm? 10. So I need to rewrite the fifth root of 10 as a 10 to some power. Again, I recognize that I can rewrite radicals as fractional exponents. So I'm just left with 1/5. How's that feel? I like doing it this way. It feels more natural to me. Like it reminds me of, things that we've kind of always done along the way. All right, first step. Base of the logarithm is 10. How do I rewrite 0.01 as 10 to some power?
Negative powers.
Good, yeah. So it's like scientific notation, right? So that'd be like 1 times 10 to the negative 2. Or just like 10 to the negative 2.
So would your answer just be -2?
Yes. Yeah. Is this feeling okay here, folks? So the first thing that I'm going to recognize here is that I have an ln. Remember, what does ln mean? No, it's base e. ln means log base e. And now I have e to the log base e, right? Exponent base b cancels log base b. So we're just going to be left with the 5. So if I look at the next one, we have 2 equals log of x. So I know that log of x is log base 10. So to get that x by itself, I need to cancel out the log base 10, right? What cancels out a logarithm? Yeah, an exponent base. So both sides I'm going to have 10. To the left-hand side and then 10 to the right-hand side. Is everybody okay with what I did there? So again, exponent base 10 is going to cancel log base 10. So x is just going to equal 10 squared, where x is 100. Is that okay with everybody?
Yeah, on the last problem, I thought we had said earlier ln was equal to 1.
Not the case. The natural logarithm is log base e. We said that we were going to write a script L so it doesn't look like the number 1. But it's definitely not. In fact, a logarithm cannot have base 1. It's defined that the b is positive and not equal to 1, the base of a logarithm. Okay? And then our last one here says lny is equal to 5. So again, I recognize the natural log. That's log base e. And what's going to cancel out log base e?
Exponent base E.
Excellent. Exponent base e. Notice that when I'm writing these exponent bases, I'm kind of like writing them exaggeratingly big. The reason I'm doing that is I'm trying my best to, like, when you go back and look at this again, that you don't think that I'm multiplying both sides by e, that it's a different operation. So it's e to the left-hand side and e to the right-hand side, not e times the left-hand side. Everybody's okay with that? So, or whoop, whoop. So y would just then be e to the 5th. And if you wanted the number, you could type e to the 5th into your calculator and get a decimal, but like, deh. Sure, no problem. All right. So at this point, we should start feel like we have a better grasp of like what a logarithm is, right? It's basically just like the inverse version of an exponential function. And we can use logarithms to cancel out exponent bases and then exponent bases to cancel out logarithms. What we want to do now is look at some more properties of logarithms, like how else can I manipulate logarithms, like how do I add logarithms or subtract them or, you know, multiply them or any of these kind of things. That would be the next obvious question. So I present you with these 4 properties of logarithms. Now the first 3 are really the main 3 that you'll use. The 4th one here, while still occasionally useful, is no longer as useful to you as it was to the student pre-graphing calculator or even pre-scientific calculator. Now, when I was doing this in like my Algebra 2 class back in the mid-90s, like the way you did log base 2 of 7 was we'd use the change of base formula to rewrite it as like the natural log of 7 divided by the natural log of 2. And you turn to the back of the textbook to the table of logarithms, look up the natural log of 7 and the natural log of 2, the decimal approximation in the back of your textbook, type those into your calculator and do the divide sign on it. And that's how we had to do this. It was a nightmare. You guys, as your calculators, you can just type any logarithm in and just press enter, so it's no big deal. Was not always the case. So like I used the change of base formula like all the time. You might almost never use it. Just letting you know. So the most common way for us to practice using these 2 properties, or these properties of logarithms, is via 2 types of problems. So the directions for those problems are they're expanding problems, and then condensing or sometimes compress. So the idea with expanding is you're going to take one log and turn it into many logs. You're going to like balloon it up. And condensing is you're going to take many logs and try to shrink them back down to a single log. And the tools you're going to use to do this are going to be these product, quotient, and power properties. When expanding, typically we're going to go from product or quotient property to product property to power property. And when you're condensing, you're going to do the reverse order. So power, product, quotient. And I say typically because if there's like a parenthesis or something in the problem that like indicates you need to do a different order of operations, then. But for the most part, you just follow this order. Sound good to you guys? We're going to do some expanding and condensing examples, and I'm going to be done today. We'll do the homework quiz and get out of here. Sound good? Sure. Okay. So the directions here are expand. So we have log base 3 of 4x. So when I look at my properties for logarithms, when I'm expanding, I'm going to be looking for things on the left-hand side and rewriting them on the right or with the right-hand side. When I'm condensing, I'm going to be doing the opposite. So I'm going to be looking for something like the left-hand or the right-hand side and trying to turn it into the left-hand side. Everybody's okay there? So when we're expanding, we're going to be looking inside the logarithm at this part. So the first thing I look for in an expanding problem is a quotient property. Is there any division going on inside that logarithm? Nope. So no quotient property to do. Is there any multiplication going on inside the logarithm? Yes. Where's the multiplication happening? Between the 4 and the x, right? There's really like a little time symbol in there. So I can use the product property then to rewrite this as log of 4 plus log of x. Everybody feel good there? The next thing I'm going to look for is, I'm going to look inside each of my logarithms now. I'm going to look for power properties. Do we see any exponents inside the logarithms? Now look carefully because there's one hiding. Not 1. Yeah, where is there a power of 2? Yeah, because 4 is really 2 squared, right? So there is a hiding power property there. So with constants, you have to be careful. There can be hiding product properties, like if that number was 6, 2 times 3. Or in this case, 4, 2 squared. You gotta be a little bit careful about those because they hide them on you. But I can use the power property so the exponent becomes a coefficient. And then the base of that exponent stays there. And that's as good as I can do. It's okay? Well, you missed that there were properties that we're using to do this. So again, new problem, we're expanding. So we start looking inside the logarithm. First thing we do is look to see if there's any division going on in logarithm. There is not. Okay, so the next thing we're going to look for is multiplication. Is there multiplication going on here? How many multiplication symbols are in here? There's 3 things being multiplied, but there's only 2. Oh boy, I copied it down wrong, huh? There's only 2 multiplication symbols, right? Does everybody see that? Okay. So we're going to do the product property twice. What the product property says is that multiplication inside the logarithm turns into addition outside the logarithm. So this is going to turn into log of 3 plus log of a plus log of b to the 5th. So everywhere there was a multiplication symbol just becomes a plus sign and then a new logarithm around that number. Everybody's good? So now we'll look inside each of these 3 logarithms, and we're going to look for any power properties. Do you see an exponent anywhere? Just on the b, right? Why does the 3 not matter?
Because it's not split up.
Yeah, it's a prime number. It can't be split up at all. Good. So the first 2 logarithms just stay the same. Nothing happens there. And then for the last one, the exponent becomes a coefficient, and the base of the exponent stays inside the logarithm. And that's it. So far, so good? All right, let's look at the next one. So we have the natural log of 2x over square root x cubed minus 5. So again, we start looking inside the logarithm, and we look for quotient property. Is there any division going on inside the logarithm? Definitely there is. So we're going to have log of the top minus log of the bottom. Everybody okay there? Then we'll look inside each of the new logarithms for product properties. Is there any multiplication going on inside either of the logarithms? Yes, just the first one. So the first one will become natural log 2 plus natural log x. But there's no multiplication in the second one, so that one will just stay the way it is. Now we look inside of each of the 3 logarithms, and we're going to look for power properties. Do we see any power properties? Where? So there is a power property in the third one, but it's not x to the third. It's the square root. What is the square root the same as? A 1/2 power. So the first 2 logarithms stay the same. The third logarithm, we apply the power property. You can say that, right? Now, many of us are going to be arguing that, like, hey, I still see a power in that third logarithm. Why can't I do the power property again? The reason is, if I look at the power property, the power has to be around the entire thing inside. Notice down here, that power of 3 is only attached to the x, not the minus 5. We cannot do a power property on this. If it was instead x minus 5, to the third, you could do a power property with that, but not with x to the third minus 5. Do you guys see the difference? Good. How do you guys feel about these expanding problems? No big deal? For the most part, usually once you get this, once you got it, you got it. It's not too bad. We're going to do a couple of condensing problems, and then I'm done. So if I look at the first problem, as I'm writing this down, I notice something that's kind of odd. Does anybody see what I'm noticing?
All are positive, but some are negative.
Are all the bases for the logarithms the same? No. So notice when we looked at our properties, the bases have to be the same in order to use the property. So I'm really going to treat this now as two separate problems. I'm going to treat it as like the base 5 or the base 4 problem and then the base 5 problem. Because those two are not going to be able to go together. It's like two separate problems. Everybody okay? Now, since we're condensing, we're going to be looking at the stuff going on outside the logarithm first. So let's do that. We want to start by looking for power properties because we're going in the reverse order because we're doing the reverse thing. Instead of expanding, we're condensing it all together. So for a power property, I'm going to be looking for coefficients in front of my logarithm. And I see that I have that going on twice. So the first logarithm stays the same. In the second logarithm, that coefficient of 3 becomes an exponent of 3. And in the third logarithm, that coefficient of 2 becomes an exponent of 2. Is everybody okay there? I typically never take the negatives with me. It's not wrong to do it, but like, I think it just makes things messier later on and makes confusion. I just leave, never turn a subtraction into like plus a negative and take it with me. It's not wrong to do it, but I don't think it's helpful. Next, we're going to look for product property. So for a product property, I'm looking for addition outside the logarithm. I see that. So I can use a product property on those first two logs and rewrite that as multiplication inside the logarithm. And then I look for a quotient property. So that's subtraction outside the logarithm, but the bases of my logs don't match. So I can't actually do the quotient property here. This would be as far as I can go. I couldn't get them down to a single logarithm because I have logs with two different bases. Well, then you're undoing it. Like our goal is to condense, not expand. We're going the reverse direction. So we want to end up with as few logs as possible with no coefficients rather than doing the reverse. Does it make sense?
Yeah.
Okay. Let's do one more, and then we're going to be done. So in this problem, I noticed that all the logs are the same, right? They're all natural logs, so I will be able to end this with a single log rather than two. This will all just turn into one thing. So I start the same way, looking for power properties. So the power property, I'm looking for coefficients. I see that I have 3 power properties going on. And I have to be a little bit careful with the second logarithm with how I do this. Because notice I have an AB. So that power of 3 has to apply to both the A and the B. So I think about that as quantity AB or A cubed B cubed. Is okay there? You see that what I'd had to do? Next, we're going to look for a product property. So I see that I have addition, so we should be able to do a product property. Now this is a little tricky though, because the two logarithms that are going to go together in the product property are not the second logarithm and the third logarithm. it's going to be the first and third logarithm. Because if I look at my power or my product property, the logs that I'm combining together have to be positive. So they have to be positive. Remember, I can add things in any order, so I could just easily write this as log a to the fourth plus log b squared minus log of a cubed b cubed, right? So those are the two that are going together in the product property. And then last, we'll look for quotient property. I see that I have subtraction. So that is going to allow me to write this as log of. Now, when you do the quotient property, its order is important. The negative part has to be the denominator. Everybody's okay there? And then hopefully you recognize that that a to the fourth b squared over a cubed b to the third can reduce. And it'll just become natural log AB. And we're done. So we still have a little bit more to do in this section 15.3. But at this point, you guys can do 37 through 68, and then 71 to 92. We'll have some time in class to work on this also, because this is, clearly a lot of numbers, but 10 or so of those problems are just like type it in your calculator and press enter, which is not bad, right? Those are like 3-second problems. You'll spend more time writing down your answer than you will actually thinking about it. But that's it here for today.